Swayam Prabha. Digital India. Educated India.
Good morning, everyone. So we welcome you to the last day of this Gyan program. So as you have been hearing, so a good feedback from your side. So it has been a learning experience and it is useful to you. So please take this knowledge and share it with your friends and in your institutions, maybe even to the faculty, so that they can actually build based on the inputs what we have given. So today we are going to talk about the applications of artificial intelligence for monitoring and control of autonomous factory. So we will also be giving some of the details about the artificial intelligence, because all these days we have been talking about pure manufacturing concepts, and we are also touching about the lasers almost every day. That's being mentioned, and then core manufacturing aspects. So I'm going to give some introduction to the artificial intelligence. So then we are going to tell about the concepts which we have used for the autonomous factory. Then we are going to show you how we have implemented these concepts practically in making this autonomous factory. So now artificial intelligence. So this word actually was an interesting word. So where people have been using very prominently these days. So you would have heard something like AI, ML. So ML is machine learning. So we're going to see what that is. So AI or artificial intelligence means it is the creation of the knowledge for the computers, and then make the computers or the machines to work like the human beings. So that is the basic idea. So we as a human beings, we think, then make the decisions. But computers actually, in general, earlier, before the artificial intelligence was introduced, they cannot do that. So thus, the term artificial intelligence, it refers to application of technology to perform tasks that resemble human intelligent or cognitive function. So that means it can think, it can reason, so it can have the knowledge, it can plan, then it can communicate, and also it can understand some of the things. So that's called the perception. And then it also has the capability to move and manipulate and then carry out some of the works. So that is the reason artificial intelligence is very, very important. And earlier we used to say that the computers will be like as intelligent or less than what we are going to create. But now we have some terms here. So it says that is machine learning. That means the machines can learn by themselves through experience, and they can even become more intelligent. Okay. So one day may come where probably the computers might be more intelligent than human beings. And then there will be some of the stories and novels which write that the robots will capture all the human beings and something like that. But there is a concept why we need to think like that. So artificial intelligence is making the computer to think like human beings. Then machine learning. So we are trying to give it the information and make it to learn progressively. And then it learns to do the task better every time we train it, or when we subject it for work. During that work itself, it learns and then it improves itself like the human beings do. So then we also use the term deep learning very frequently. So what is deep learning is, it is a type of machine learning that runs inputs through a biologically inspired neural networks. So mostly we'll be using a lot of hidden layers, and then we call them as convolutional networks, CNNs, and then we give a lot of data to it, and then we make it to mimic like the human beings. So there is knowledge which will be called, or intelligence which will be called as shallow knowledge, and then deep knowledge. So shallow means, I think even in human beings we say, so sometimes when we conduct viva to the students, when they do a work, we conduct the viva, then ask few questions. So in that we understand whether that student or the person has depth of knowledge, or simply he knows only few things. So that we can understand. So similarly, even for artificial intelligence systems, so we have like shallow knowledge and then deep knowledge. Deep understanding means it can think better, make the right decisions, even when the situations which are posed are something different from what it has already seen or what has been programmed. So if they can still make the decision, so we tell it as the deep knowledge. So thus sometimes even they can overcome, or it can overrule the predictions which is made and then take a decision. So the deep learning is like a more intelligent person with a deeper knowledge. And then how do we achieve these machine learning techniques? So usually there are three types. One is called as a supervised learning, second one is unsupervised learning, and third one is called as an reinforcement learning. So what we do in supervised learning is like if there is a trainer or a supervisor, so we'll be asking us to do the work. So if we do it correctly, probably they'll give us a reward. And then maybe you would have seen some places when they do something wrong, you give a punishment or something so that they will not do that. So thus there'll be a supervisor, so which will actually guide them, and through that process they can do it better every time. And that is generally done by in the computers by what is called as a labeled data. So for example, if my machine learning is analyzing the defects in a machine part, okay, I can tell a component, and then I'm asking it to check whether it is good or defective. So then what we do is we give the picture of the good one and then say, so this is correct. And then if there is a defective one, so we say that this is defective, and train that neural networks. So then it knows where to award or where to then give the punishment, means remove the awards. Then in this process, it actually learns to make the things better. Then unsupervised learning. So generally like we send some people to do a work and we don't give much of the instructions. So they learn by making their own mistakes. So then probably when they make a mistake, something is broken, so they lose the money. So then they learn and finally they come to a level so where they become better. So reinforcement learning is learning from the past experience, and it tries to capture the best possible knowledge to make even a better or accurate decisions. And in deep learning process, what we do is we try to understand the problem, and we can't generally apply deep learning to every problem. So we need to look at the problem, whether it needs shallow knowledge or deep knowledge, and only in that cases we try to apply the deep learning. Otherwise the system becomes too complicated, but finally what we achieve will be nothing. Then we need to identify the relevant data sets and then prepare them for analysis. So like if there is an image, there might be something, noise will be there, unnecessary data will be there, so that pre-processing should be done. And then we need to choose the correct algorithms which is suitable for a particular problem, and then work with it. So then train the algorithm on large amount of labeled data so that it learns better, and then finally test our models. So this is the way how the artificial intelligent systems work. So we have AI, ML, and then the deep learning. So these are all part of the newer technologies which have been developed recently, and they have been applied to almost every field. So here, whatever we have given is just a sample of that, but the artificial intelligence can be almost given to every device or every system. So even the cameras, what we use, so they have become intelligent. So earlier, if you see manually, we need to focus and then take a picture. But now, so they automatically adjust. And then if they are more intelligent, they also show you a face, so where it need to be focused and which are not necessary. So all these things are possible. So right from a simple product to a complete system, we can apply artificial intelligence. Like aerospace field, I think several flight simulators are being used. Actually, I'm here in US, so where we have NASA, space organization. So in Houston, so there they use a lot of these kind of simulators. So when we went for visiting there, so they gave us an experience. And so where artificial intelligence plays actually a very important role. And also the driverless vehicles, both even for programming with the aircrafts or even in the automobiles. So we have actually sat on those kind of Tesla and other cars. So where driver don't need to touch the steering wheel also, you can just program and then leave it. So we'll be actually seeing a scanner going around and then trying to identify if there are any obstacles. And then if something is there, automatically it brakes. And then some of these vehicles, what they do is when we are driving a long time, just to make sure that the driver is present and he is alert. So it will give a beep and then says that touch the steering wheel. So we need to just touch it. That's it, to make sure that we are there. And the remaining part, it takes care. And mostly on the highway, so it is easy. And so when we had some Indian visitors and all, they were afraid. They are telling that, oh, please hold the steering wheel, because in India sometimes we do and then accidents happen. But here, the intelligence is actually controlling, looking at all the surroundings, and then so it is driving. It's so self-driving cars and all these things need a lot of intelligence. And robotics is another field where the artificial intelligence is synonymous. So sometimes when you say robot, they think that, okay, it has artificial intelligence. So thus they become almost like a synonymous with artificial intelligence. So then we have virtual factories, and then we have what is called as a digital twins, which will be telling you. So then even in the other areas like smart cities, so now people are being developing all the artificial intelligence systems to make the buildings smart and the cities smart, and probably the whole world more smarter. Okay, so now our interest is in the area of manufacturing, and we have been actually applying this artificial intelligence to our manufacturing area. So many times when we say mechanical engineering or manufacturing, people think that it is more to deal with only machines and hardware, but it is not. So nowadays, actually, even when we started talking about all the AI, ML, digital twin, and all these concepts, so more people were being attracted to this branch. And also we have found that for our project, I think you have already visited the autonomous factory, so I'm able to tell this right at this stage. So when we wanted to like hire some of the project staff, we invited the computer science students and then asked them to see the factory and then do the tasks. Then they found it very difficult actually to understand the CNC machines, the robots, or the other things. They were very good with the concepts, but implementing became difficult. So then later, what we did is actually we hired mechanical engineers and then taught them the computer science and all these AI principles, and they were able to do the tasks. So maybe when you visited and when you spoke to the people there, so we are all mechanical engineers. So thus mechanical engineering has a lot of scope where we can apply the artificial intelligence to our own field. So now one requirement to apply the artificial intelligence principles to manufacturing, first we need to make it as a digital manufacturing. So as long as you have a lathe machine which is like very mechanical, and then there are no sensors, no CNC or anything, you can't make it like automated. So if you want, that is a hard automation was there, but that is very like a mechanical kind of an hardware where you can set the limit switches and then put a reverse so that something moving forward can go back and then move. So that is an hard automation, it is called. But now what we are talking about is the soft automation. So where with the computer programs, we can control the machines and change the task what they are making and all those things. So this is more flexible. So now what I would like to say here is that to implement the AI principles, first we need to make the factory as a digital factory, or the whole manufacturing as digital manufacturing. So wherein the whole factory need to be digitized and then put it into the computer. And here even the graphics actually plays an important role. So we can even create the graphics in such a way that we can see the whole factory on the computer, on the monitor in the computer. And also we can also see how the work is flowing, workpiece is moving, and all these things is possible. So first we need to make that. Now once we have made that, then we wanted to define what is called as the autonomous factory. Why? Because earlier to this stage, we had what is called as automation. Okay. So we had automation, but now here what we are talking is autonomous factories. Maybe the participants, can you say, is it same or it is different? Automation and autonomous. Is it same or they are different? What do you think?
So they are different because if we talk about automation, we are just doing some programmed tasks. But in case of an autonomous factory or an autonomous system, it is with complete or no human interference, and even decision making is done to some extent in those systems. So that's the main difference.
Yeah, that's right. So you're precisely correct. So in automation, what we were doing is, it is mostly the programmable automation. So where we program the machines, so they carry out the task. That's it. But that is good because we can get high production rate, we get more accuracy, the quality is controlled, and then consistency is maintained. So that was good for that generation. But now what has happened is we have moved on to the next level where we want the factory itself, so the components in the factory itself, to make the decisions. So that may look a little challenging, but there was an introduction of what is called as cyber physical systems and IoT. So does anyone know what is an IoT? cyber physical systems, IoT?
IoT basically is Internet of Things.
Yeah. So what does it do in Internet of Things? So things, how they can make,
So
how can you connect?
IoT basically is like wireless connection between the sensors and the platform or the computer. So IoT will collect the data from the sensor and then send it through the and then send it to the computer. Then the computer or platform will make the decision according to this data.
Okay. Yeah. Thank you. So here in the earlier generation, we had network of the computers. So the computers were actually a network. So that is possible. But in this, what we are talking is Internet of Things. Things means it can be a light, it can be an air conditioner, it can be a washing machine, or anything. Okay. So now, how can we make them to communicate to each other? And also they need to communicate with the human beings. So now probably you would have seen some of the lights in a room. So when you walk in, so they get turned on. So how is it possible? That means there is a sensor. So it can be a motion sensor, or it can be a sound sensor, acoustics, or it can be even thermal sensors. So wherever as required, and as you move, so the motion is detected and the light gets turned on. So now that means light is not actually a computer, but it is a thing, but still it is able to communicate. And that is actually done through the sensors. So thus all these machines, whatever we are talking about, they should have the sensors so that they'll be able to communicate among themselves and even with the human beings. So these things have become necessary, and we call them as the smart. So now you can put the sensors and then make them sensitive and then smart. So these are required, and we are going to talk about how we'll be able to make these kind of autonomous factories and what will be their benefits. So now, if you look at the factories, they are actually a complex. So it is not one task, there'll be several tasks which will be taking place, and then they need to carry out different complex tasks. The coordination between each of them is important. And then the real-time position and the status is also plays a important role. So for doing that one, actually we have all these sensors. So once we have them, we can monitor them, and also we can actually take the right decision making. It's almost in real time. So we actually see even our factory also that is possible with a just maybe few microseconds of lag. So now we'll be looking at with these concepts how we were able to implement the factory which you have seen. So this we have done a project for one of the company called Accenture. So in IIT Research Park, we would have gone, we would have seen one of the initiative of the government. It's called Pravartak, so which encourages innovation. So something new if you want to do. So it is not only faculty, even the students or anyone. So if they want to do something new, so they provide the space and some funding and other facilities. So the environment so that you can learn and then do something new. Okay, so under this initiative, we have built this autonomous factory. So you see the actual factory here and then digital factory. So how we have implemented that. So those details we are going to give. And before giving that, we want to make sure that you understand what is called as the digital twin, because so we build this autonomous factory using the digital twins. So what are these digital twins? So digital twins are nothing but the digital replica of the physical systems. So what is a twin? Twin means probably if you have seen the twin children, so once one baby cries, even the other baby cry. So if a baby gets cold, other baby also gets cold. So that means if one behaves like this, the other also actually behaves similarly. So here what happens is if we build a digital replica of the physical system, the way how physical system behaves, the digital system also behaves. The way how digital system behaves, so that will happen actually even really. So thus even prediction, modeling, and all these things are possible with the digital model. So little more details about what is this digital twins. Earlier and many times this question will be asked even when we present these concepts. So they ask, yeah, we have like a modeling. So what is the difference between a model and a digital twin? So here this picture probably will be able to tell what is a model. So usually we have a physical system, and in modeling what we do is we make actually a model of the physical system, but there is no direct link between the physical object and modeling. So probably in modeling we can run some simulations, but then we need to go and physically probably set the parameters and run that system. Okay, so that is a model. So there is no interaction directly between the physical model and the digital or the digital model. And then we have another term which is called as a digital shadow. So where whatever the changes happens in the physical system, so that get actually reflected in the digital model also. So that is the digital shadow. But then digital twin means it is linked both the ways. So this is linked and the digital object is also linked to the physical. So anything's happen here gets reflected, or anything you want, if like for example, if I have a jet engine, so which I want to predict what is going to happen when I run for next 100 hours. So now I can run those simulations here, and finally if we run, actually the same thing happens to the physical object. So it's going to fail, means it will really fail. And if this is a machine for which we have made a digital twin, if there is any tool here, so the digital twin actually gets updated. So it knows that the tool is worn out. Or if the temperature is increased, so the digital twin also shows the temperature being increased. How it is possible? It is with the sensors and then the controls. So thus sensing and controlling is important almost on the real time. So few more three things I need to tell before we proceed. The digital twins, you can make them like at a system level. Okay. So that means now we have done it for an autonomous factory. That means the factory is a system. Okay. So we can make the digital twin of it. Then we can also make the digital twin of a process. So a process means like I have a cutting process, turning process, milling process, or maybe a grinding process. So we can actually make the digital twin of that process. But there is a big challenge in doing that. So whatever our experience, through our experience, you can say that making a system twin is more easier, but making a process twin is more difficult. So why? Because if I need to make a simple turning process for the digital twin, I need to understand the mechanics of the material removal and all the principles, and then only I'll be able to make it to behave same as the physical system. But then there is another way of doing that which I don't recommend. So that is called as a black box models. So what they do is they say that you have a physical mechanism which is happening. So say turning process. Why do I need to understand this process? I don't want to understand, but still I'll be able to tell you when you increase the feed, what is going to happen. When you decrease the speed, what is going to happen. So how do they do it is that they conduct several experiments, collect the data, and then based on the data, you make a model. So now we didn't understand the science or physics of the process, but still with the help of data, you change the parameters, input parameters, it gives the change in the output parameters, and physically when you implement them, almost it is right. But okay, so some people are happy with that, but it is, though it is, we don't understand the process, so that's why we called it as a black box model. So that is process modeling. Then another modeling what we can do is a product model. So that can be something like a jet engine is one example, or a camera system, or even a cell phone, or any one product you can take, and then you can make the digital twin of it. So when you make this digital twin, so we have several advantages. So many of them have been listed here. So something like what you can see is the data visualization. So you can see the data coming, or if the temperatures are increasing, you can see the graph going up or the color changing. So you have physically, you can visualize what is really happening in the physical world. Then real-time synchronization with the physical system. Then see, we used to talk about different types of maintenance. Earlier, it is what is called as a breakdown maintenance. So you run the machine till it breaks down. When it breaks down, you go check what has failed and then replace. But that is actually nowadays it is not recommended, because when it fails, the whole process need to stop. So sometimes if you are working with a very lean the stocks, so once you stop, that whole process need to be stopped. So nowadays we are not keeping a lot of stocks, but we run on a lean manufacturing kind of systems. So that means in the breakdown maintenance, you cannot follow. So then it is prognostics. So where we understand it and then do the maintenance. So here we have what is also called as a proactive kind of a maintenance. So where before the machine fails, so we can actually maintain. So thus we can also optimize. Then simulation and training we can do right on these machines. So flight simulator is one of the best example. So where you cannot give a trainer a flight and ask him to run and then learn. Maybe driving on a road, it might be more easier, but you can't give a flight. But how do you make them to learn and feel what happens when you run a flight? So that can be done by using the simulators. Then fault detection, and then how we can respond, then scalability, then workflow, coordination and automation. So there may be several tasks which will be simultaneously made. We need to coordinate. Then we can do all these tasks with minimum human intervention. Maybe at some stage you can also say without any intervention of human beings. Then remote control and automation. So nowadays we are using another technology, what is called as a cloud. So wherein the whole data and also the processing can be done in the cloud. That means we don't need to be done it in the computer, what we are doing. Though we have a technology nowadays which is called as an edge technology. So where we do it at the place where you get the data. But cloud means it is not in our hardware, but it is in some other place. So like I'll tell you what are the softwares we have used for the cloud computing. And obviously we have several advantages of using them. So for implementation of these digital twins, we need sensors, data loggers, computers, communication networks, and then data processing. So all these things will be integral part. So any question?
Sir, can you please differentiate between digital twin and digital shadow?
Yeah. Okay, so here you can see the lines. So dotted lines, I don't know if you are able to clearly see that. So dotted lines means manual data flow. So this is actually a dotted line. And then this is a thick line. That means data can flow from object to the digital object. So the digital replica, but we will not be able to send the data from the model or the digital shadow to the physical system. So we need to do it physically. Like for example, so if I predict something here and then say that, okay, I need to set the parameters at this level. So the digital object will not be able to direct or tell directly the physical object to do that. So we need manually, we need to note down those numbers, go to the machine and enter them and make it to work. But digital twin means now the object can directly communicate with the physical system and then tell you change. How? I'll tell you the example with our smart factory. If you have a robot, think that we have a robot. So now, if the machine has completed a job, the machine will tell the robot, now pick up the workpiece. Then what robot will do is it will pick up. So then it will tell to the AGV to come to this position so that I can place the workpiece on you and you move to the station 2. So that means, so the digital model itself is able to communicate to the physical systems and then make it to work. So these are both are dark lines. That means the data flow from the physical object, it goes to the digital object, and digital object can actually talk or instruct the physical system. Am I clear?
Yes, sir. Sir, then another doubt. While speaking about that autonomous factory, factory can contain both digital twin as well as digital shadow, or is it specified to only digital twin?
Yeah. So actually, autonomous factory means that can take decisions independently. So now, for example, if I have an autonomous factory with a digital shadow, okay, whatever is happening physically, my model gets updated and then it takes a decision. Then what happens? So we'll not be able to implement again, human intervention is required. So that is the reason we said that if we have the digital twin, so the human intervention can be minimized. So otherwise what will happen is it's autonomous, it has taken a decision, but how can it implement? So that it will not be able to do. And again, some manual intervention is required. So thus up to this part, it can be autonomous, but implementation, we have difficulties.
Yes, sir. Understood. Thank you.
Yeah. So,
Sir, I have
just
one word.
yeah, you have another question? Yeah,
Yeah.
please do.
So, as part of the autonomous factory, is it advisable to have a measurement step as well during the factory functions? Like in our typical project that has been done with Accenture, we saw a robo and CNC machine integrated into the autonomous factory. So, is it okay to include a measurement or a part inspection process as well in the autonomous factory?
Yeah. So we can actually introduce that. So, and another important concept what we need to do is, I think you might have studied in quality control and other things. We have a process. So if the process is under control, so we can actually make sure that the product which comes out of it is good. Okay. So if the process is out of control, the product quality will not be good. So probably you need to inspect that and then to make sure that your product is right. But if my process is, if I can trust the process, so then I can make sure that the product which is coming out of it is good. Okay. But in many cases, actually, we can use the data from the inspection systems and directly integrate it so that the process can be even more improved. See now, for example, if I'm turning a part, think that due to the tool wear, so the dimension is increasing. So in turning, actually, if the tool becomes smaller, the dimension becomes bigger. So then if I'd had a inspection step there, so I can get the data and then send it back to the machine. And then what it will do is, if it is not micrometer, but maybe 100 micrometers, if it is worn out, I'll make the tool to move further so that the size finally what I'm getting is same as what is required. So that step is required. But in our factory, we didn't use that still. But at some stage, we'll be putting a measurement system so where it will give the feedback directly to the digital twin, and if any implementation is required, it can actually tell to the machines.
Thank you.
Yeah. These metrology concepts, actually earlier it is something used to be like an offline, but now metrology became an integral part of manufacturing. So measurements and metrology has become an integral part of manufacturing. And also it is a feedback loop. So the loop is actually completed. It is not just inspect and then say the part is wrong, then throw it away, reject it. No, that is not the thing. We need to get the information from it, why it happened, and then give it back to the system. And also we have what is called as the in-process inspection. So where during the process itself, we'll be able to inspect the part and say that something is going wrong. Before going wrong, we can actually set it right. So that is called in-process inspection.
Thank you, sir.
Okay, so yeah. Was there a question? Okay, so the digital twin history is very interesting. Actually, in 1970s, so the NASA engineers here so have made a physical twin. So because like if you want to send the astronauts, so we need to make them to understand what is zero gravity. Okay, so but we cannot take them to the space, but then make a physical system and make it zero gravity, put the people there, so then they can experience it. So that is actually a physical twin of it. So we have actually seen those modules, so where the people go in, but we are not allowed to enter there. But from a distance, actually, they show those modules. So where there'll be a zero gravity they can create, and then astronauts can experience. So here, even in our institute, there are people who are astronauts, but now teaching in the university. So they talk about a lot of such kind of an experience. So from that physical systems, then the term actually was introduced, which is a digital twin. So, okay, from the physical twin, it became a digital twin. So then all the technologies actually contributed. And finally, now we have what is called as the digital twins. And then they are trying to standardize and make them implementable. So now for our factory, as you have seen, so we took these 4 machines, like a CNC machine, a 3D printer, 2 robots, and then 1 AMR. So AMR is automated mobile robot. So the little lower version of that, we used to call it as an AGV, automated guided vehicles. But generally it used to have a wire guided or magnetic guided or paint guided. That means you put a path and then ask it to go only on that path. That is an automated guided vehicle. But this AMR, you don't need to have that kind of a path or wire which is laid in the floor, but it can actually decide its own path, and it can detect the obstacles, and also it can interact with the other systems. So we call this as autonomous mobile robot. More than automated, it's more autonomous mobile robot. So this is the physical system which already you have visited. Actually, setting up the physical system has its own challenges, but that was looking more easier than the next steps. So where we have implemented the digital twin. But here we also need to note that when we use these machines, we need to have a lot of sensors in it. But initially, when we bought these machines, there were no such kind of sensors, but we have implemented. So we have actually implemented the force sensors, so the spindle sensors, the current sensors, and all these things, so that we'll be able to get that information and then get to the digital twin. So that's the sensors have been incorporated. And then if you look at the 3D printer, so even the door opening and closing, actually we automated. It looks little odd, but we need to implement because we don't want to open the door to the side. So we had a space. So we customized it and made the door to move up and down so that it can close and open. And this chamber is actually heated chamber. We can know what is the temperature inside that. And then the bed is actually a geometrically balanced bed where we can know what is the level, and we use the 3 points to make a plane and then to level it. And there are IR cameras and other cameras. We have been implementing it so that we can see what is happening and what will be the thermal profile, like when printing it, what is the temperature and what is going to happen if this temperature is there. Am I going to get a good product, or I need to change the temperature? And all these things are possible. And similarly on the robots, the tactile or tessile, how do you call? So sensors have been implemented, and robots, even cameras, we can put it here so that they can see where the objects are there, and all these things have been done. Now coming to implementation of the digital twin. So a lot of details are there, but I don't expect you understand all of them, but at least some of the concepts, if you understand, I think that should be fine. So usually when you look at the architecture of these autonomous factories, so we have the physical system. So then we need to have a digital twin layer. So where we had to make the digital twins. Now the problem will be when you have a CNC machine, the controller is different. So the coordinates will be different. And then if you come to a robot, so that controller will be another one. And then their coordinate positions, if you take out the data and see, so those numbers will be different. But now then again, we have an AGV, which is also again, it has its own coordinates, but we need to bring them to a global kind of a coordinate so that each will be able to know where it is and where it need to move. And the collaboration between each of these machines is the biggest challenge. And we also had a challenge that most of these machines, when they make, they will not give all the data, and also we cannot actually input our own inputs to that machine. But then we talk to the manufacturers of the company. So they have been generous enough to give us the data since we are using it for research. So they gave. So thus we are able to develop a collaborative layer where each of these digital twins can interact with themselves. And finally, they will be interacting with the physical layer. So we have physical layer, intermediate digital twin layer, and then the collaborative layer. Okay, then as I said, we have what is called as a cloud computing. So wherein the computation or the storage of data doesn't happen on the hard disk like what we have in our computer, but actually it is connected to the net and the servers will be somewhere. Okay, so now one example like AWS, Amazon Web Services. So when you take that, Amazon have their servers somewhere. But we access that through the net. And that is the reason it is called as a cloud. Cloud storage means some data you put it somewhere else, not in your computer or in your hard disk. So then processing that data It's not happening in our computer process, but it is happening over the network. So these are called as the cloud services. So there were different providers for this. So Amazon is one, then Microsoft with a name called Azure, they have web services. Then Google also have cloud services. Then IBM, Oracle, and all these companies have. But finally, for our purpose, we selected Amazon Web Services. And then to make the graphical platform, so which you would have seen when you visited the autonomous factory, I'll also be showing you the video. So wherein it looks like the real factory, but how do you make them? So there are some of these platforms. They are more than a software, like they are more a platform kind of a software. So by using which we can do that, we have different ones. So Unity is the one which we have used. In fact, these softwares or the platforms are more used for gaming purpose. So for gaming, actually, you need a lot of competition and graphics. So they used, but now we are using it for actually more technical purposes. So then we are also actually looking to implement this on NVIDIA Omniverse. So they have their own advantages, disadvantages, and other things. So those platforms play a very important role. Okay. So similarly, I'm not going to explain all these things, but I'll tell you what we have done. So working of the collaboration layer, how each of them were able to connect themselves, then with the help of the data which is put in the web services, we were able to implement that. Then while implementing it, initially we had the local control only to the factory, but then by implementing what is called as a WebGL, web graphics library, so we are able to make it on a cloud. And the advantage is that you can be anywhere in the world, but still you'll be able to access that and then look at the data, what is happening. So we have also actually kept a camera, so where we can see the physical thing, and also we can see the digital twin happening right on the computer wherever we are in the world. So that is actually made possible. So this is the digital twin of the factory with the dashboard. So we can actually click on these symbols, and then actually they can move, and then you can see the dashboards. So autonomous mobile robot or robot, you click on that. So they go to that particular menu, like click on CNC. So the whole menu will be coming, and then we can see the whole data in the video. I'll show you. So even the surface finish or tool wear, dimensional errors, feed rate, cycle status, temperatures, XYZ positions, spindle speed, spindle load, spindle temperature. So all this data, we are actually extracting it from the machine, and they will be displayed dynamically. So you can see that every millisecond it gets updated. So similarly for the 3D printer, the position, the nozzle temperature, the bed temperature, the chamber temperature, then printing speed, the time which it has already taken, and then print status, whether it is going on and its no work is there or completed, the humidity, the type of filament what is used, and its weight, and all these things actually we can see it on the dashboard running, and we'll be able to actually even interact. So now if you say open the door, it gets opened. You click on this close, means it closes. So either manually you can do, or the digital twins can interact and then do by themselves. And similarly for autonomous mobile robot, so we have made this dashboard, and then through this we'll be able to interact, or even they can interact among themselves. So XYZ positions, orientations, errors. So the camera which you are looking at, first camera or second camera, like that. So all these things. Okay. Yeah, is it clear? Any questions or doubts? Okay, fine. So, if you don't have doubts, I may not go into depth of these details. So, hope you already got an idea. So, it was a tedious work actually to implement these principles, whatever I have explained. Implementing them is not that easy. So, we have taken this CNC machine, and then later we have put all these sensors on them. Then, as I said, the challenge is that getting the data from the sensors and then integrating them and then send the commands to the CNC machine. So, all these things are difficult. So, probably if you have worked with these machines, you know how difficult it is actually to send these commands, and that too automatically. So, even the workpiece clamping system, we have made it automated, vibration and temperature sensors. So IoT and PLC devices which are required for connection, data processing, and all these things. The sampling rate what we have used is like 100 milliseconds. That means so every 100 milliseconds will be getting the data from these machines, and the computer keeps updating it. So you can see that in the panel. So spindle speed, load, temperature, feed rate, axis positions, then even the current of the motor, the power, the motor which is driving X, Y, Z axis, we can see, and then which tool is actually is being used, and vibration, temperature, all these things we can get it. Okay, so I don't want to go into too much of details. Most of the part is more like a theoretical part of it. So this is what has been the steps which have been used for implementation. So this is the architecture. So as I have explained earlier, so this will always have a physical layer, an intermediate layer, and then a collaborative layer. And then that whole thing connected to the local server, and then through that to the web server. So this is the general architecture which has been used. And as I said, we have used the Unity for making the graphical representation of these machines, the 3D graphics, and the platform what we have used is the Unity. And even the manufacturers were generous enough to give us the CAD files and other things. Otherwise, it's very, very time consuming even to make the machine to exactly to look like the physical machine. That itself will take a long time. So I think I'm not going to give you these details. So you can see the digital twin of the CNC machine. So on the left side is the digital twin, and the right side is the actual physical system. You can see the XYZ position changing whenever position changes. So when this is moving, you can also see here the x-axis moving. And the numbers here, you can see y-axis position has changed. So the stage is moving, so really also it is moving. So you can actually look at various angles from various angles. So the camera positions actually can be changed. That means that digitally the camera position. Okay, so the actual physical camera is not focused properly. The door has got opened and there is a small lag. Yeah, so there's, yeah, similarly, I think from another angle, you. Okay, so finally, probably will show you the full coordination of all the machines. So thus we made the digital twin of the CNC machine, then the digital twin of the printer, so with different parameters, and this is the dashboard, so through which we can actually interface. And even this, actually, the manufacturers were generous enough to give us a lot of freedom to manipulate all these numbers and then to directly input them so that we can control the machine. So bed leveling is another interesting thing. So we know that there are 3 points which will be required to make a plane, and that actually can be done. So probably we can see how it moves, and then it's not printing, it's before printing. So leveling them, adjusting the levels. So it has a sensor, so which will touch and then knows where it need to lower it or increase the height so that the bed will be to the right level. So similarly, as we have shown for CNC machine, the physical layer, the intermediate layer, then the collaborative layer, finally a connection to the web servers. Yeah, so this is the dashboard and it's the system. When the bed is moving, actually here digital twin also moves. I think we have not mounted the camera on the stand, so there is a little problem there. Okay, the physical video, I think we'll be taking even more professional video of it. That is the dashboard on the machine. Even the machine also we can actually see. When it is printing, we can see what position, where it is. Yeah. So similarly, for the autonomous mobile robot, actually we had a lot of difficulties with autonomous mobile robot because the resolution of the autonomous mobile robot was not that high. And then when you put a workpiece there, sometimes the robot was catching somewhere else because the coordinates were not exact. And then the turning and angle. So later, our students, actually interns, so they wrote the algorithms, then made the corrections, and made it actually to get the exact coordinates of the system. So our project staff are also worked on that a lot to make it, to bring it to the resolution equivalent to the robots. So usually robots are more like a precise because you want to place that object on the machine. So they are designed with a higher precision. But these autonomous robot vehicles they travel for a longer distance. So you cannot have that kind of a precise positioning. So there was a non-compatibility between these things. But then later we were able to correct that. Okay, so this is the one, and yeah, we had a lot of challenges done. So similarly, even the robot, it has been implemented. So the coordination between each of the robot, and then picking from the AGV, placing it on the machines. So that is all required a lot of coordination. So once the AGV has come, so the door gets opened, the robot goes and picks up the part, which assume that it's already printed. Actually, we changed even the design and height of the 3D printer to accommodate the robotic arm to go inside and then pick it up. So this is called as a machine tending operation. So where you feed or the workpiece or take out the workpiece. It goes to the next position. So then the robot will pick it up and place it on the CNC machine for what is called as the post processing of the 3D printed parts. So then clamping also will be done automatically. So initially, actually, when we had the 3D printed component and then made the automatic clamping, so the clamping pressure was so high that the workpiece was crushed. But then later we need to put the sensors, and we had to tell them that only this much is the pressure you can apply. So otherwise it can even crush the workpieces. So then the machining cycle starts. Okay, so that's with all these things. So finally, we have made the digital twin of the whole factory. So where all the sequence of the operations will be done automatically. Yeah. So we have a lot of scope for these kind of a digital twins. So we can have real-time monitoring, performance optimization, predictive maintenance, then collaborative decision making, resource allocation, machine allocations, remote monitoring and control, defect detection, and then controlling, then customization, and we have a lot of flexibility. So these are all the advantages. Okay, so thank you very much for your attention. So if you have any questions, you can ask. Otherwise,
what is the limitation of digital twins in autonomous factories?
Limitations means actually, see now we have a lot of challenges. So it is not actually, even till now, it's not fully complete. So tune it to the real system, we have still a challenge. And then while implementing them and making them fully autonomous without human intervention, so that is still there are several steps we need to carry out. And sometimes in the practical industries, when they try to implement, it is little expensive. So it is more feasible to implement for a product. But if you have to make it on the system level, so whole factory, if you want to make autonomous, so it will be very, very expensive. So cost is one of the limitations, and even some of the technology now to bring every system to the digital twin, and then to make it to interact among themselves and to instruct the machines, that is the physical systems. So it is 100% making them is a big challenge. Now what we have done is actually still it is a smaller part. Now if I need to make the whole system fully autonomous, even I need to make the process model of it, and then the product model, process model, and then I need to come to the system modeling. So that's all still a evaluate. It is going on. So it is not complete, but it is under the process. At least that is the reason we call our factory as a demonstration. That's all. We are trying to show the concepts and demonstrate it. But practically implementing, we are actually contacting different customers, and when they give it, so we need to see how in the real world it works. So at laboratory level, we have demonstrated it, but taking to the actual shop, implementation always have a challenges. Yeah, I think if you don't have any questions, we'll stop here. Thank you and wish you all the best. Thanks for taking all your efforts and coming to IIT. And then learning. Please use this knowledge in your life, in your career, and disseminate it to other people so that we'll have more knowledge. I think Government of India, even IIT, are all taking a lot of efforts actually to take these technologies to the next level. So in the world, we have missed several technologies like IC, manufacturing of ICs, integrated circuits and all. So, but now we don't want to miss that kind of a thing. So thus, whatever technology comes, or governments are supporting us so that we'll be able to implement them in India. So you are the younger generation. So you are the next generation people who need to take these technologies forward. So we don't know what you're going to become in future. I'm sure with these inputs, you will do well in your career. So wish you all the best. Thank you.